This is a question from GATE 2017 from Chemical Engineering, question number 46. The C curve measured during a pulse tracer experiment is shown below. In the figure, C of T is the concentration of the tracer measured at the reactor exit in mole per liter at time T seconds. The mean residence time in the reactor rounded off to one decimal place is dash seconds. So this is a question from residence time distribution from non-ideal reactors in chemical reaction engineering, and the reference NPTEL series can be found in module 1 lecture 53 RTD for various reactors part 2 chemical reaction engineering 1 homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question we have been given a C versus T plot for a particular pulse tracer experiment, and we need to find the mean residence time T bar, and the T bar can be found as integral 0 to T into E of T dt, 0 to infinity. So here let us divide this curve into two. So redrawing this curve, we had this was our RTD for 0, 1, 2, 3. So up to time 3 seconds. This was the concentration versus time curve. So what we can do is we can divide this concentration versus time curve into three parts. So this will be part 1, this is part 2, and this is part 3. So our mean residence time is given by integral 0 to infinity T into E of T dt. So just a second. Okay, sorry about that. So now the thing is we have the C versus T curve. So what we need to know that E of T will be C by integral 0 to infinity C of T dt. So from this question, the area, so this is one. So we need to find the E curve first so that we can apply this formula here. So here this the value of E can be C of T divided by area under the C curve. So area under the C curve will be 1 by 2 into base into height, which is 2 into 1, and that is equal to 1. So what this exactly means is E of T, just a second. Hey, sorry about that. Had to answer the door basically. So yeah. So okay. So now what this essentially means is E of t will be equal to C of t by 1, and that is C of t. Or in other words, E curve will be pretty much the same as the C curve because the area under the curve is 1. So our E curve will also be like this. So this will be our E curve. And here also what we'll do is, as we intended before, we will split this E curve into 3. This is part 1, this is part 2, and this will be part 3. Okay. So the mean residence time T bar is equal to integral 0 to infinity T E of t dt will become, integral T E of t dt for part 1 plus integral for part 2 plus the same integral for part 3, right? The residence time T bar will be a sum of the integral T E of t dt for part 1 plus integral T of t E of t dt part 2 plus integral T E of t dt part 3. So now what we have to do is we have to find E of t for part 1, part 2 and part 3. Okay. So from the figure for part 1, it is basically a straight line like this from 0 to 1 in the x-axis and 0 to 1 in the y-axis. And we can represent this line in the form of y equal to mx, right? So here y is E of t and x is t. So E will be equal to m into t. Here the slope is basically 1. So this curve or this line can be represented as E of t, which is equal to t. So let us say this is for part 1. Now similarly, we can do the same for part 2. Now in part 2, this is from 1 to 2, and the x-axis is t and y-axis is e, that goes from 0 to 1. So this equation can also be represented as y equal to mx plus c. So here y is e and m again is the slope, and that is minus 1. So minus x plus c. C is the intercept, and this will intercept the y-axis at 2. So E of t for part 2 will basically be 2 minus t. Now move on to part 3. So for part 1 we had E of t as t. Then for part 2 we had E of t as 2 minus t. Now part 3, E of t is basically 0 because it just coincides with the x-axis t, and E of t for this line will be 0. So E of t for part 3 will be 0. So now getting back to our formula, mean residence time t bar is equal to integral of 0 to infinity t e of t dt, and we had divided this into part 1, part 2 and part 3. So this will be integral 0 to 1 t e of t dt for part where e of t is the e of t from part 1. Then this is added to integral 1 to 2 t of t into e of t dt for part 2 plus integral 2 to 3 t e of t dt for part 3. Now e of t for part 3 is basically 0, so the third term will get cancelled. So now what we can do is we can substitute the e of t's from part 1 and part 2 into this equation. So mean residence time t bar will become integral 0 to 1 t into e of t for part 1 is t and e of t for part 2 is 2 minus t. So we'll substitute that here. This will be 0 to 1 integral 0 to 1 t into t dt plus integral 1 to 2 t into 2 minus t dt. So this will be our final integral equation. So now all we have to do is integrate the equation and apply limits. So t bar is 0 to 1 t square dt plus integral 1 to 2 2t minus t square dt. So this will be integral t cube, this will be t cube by 3 from 0 to 1 plus 2 t square by 2 minus t cube by 3 from 2 to 1. So now if we apply the limits, this will be 1 by 3 minus 0 plus 2 into t square, that is 2 square by 2 minus 2 into 1 square by 2 minus t cube by 3, applying from 2 to 1, that will be 2 cube by 3 minus 1 cube by 3. And if we do this mathematical operation here, we'll get the final residence time t bar is equal to 1 second. So the required mean residence distribution time here will be 1 second. A shortcut for this can be, because this residence time distribution has an identical geometry like this, we can say that the point at which both the part 1 and part 2 becomes identical, which is the halfway point of this triangle, that will be our mean residence time t bar. And from the graph, it is at this point. And that means the mean residence time at this point will be 1 second. So this is like a shortcut method to find the mean residence time for residence time distribution that has identical geometries.